All right, in this problem, we've got a pump that we need to calculate the power requirements for. This pump is taking oil from this reservoir, reservoir A, and pumping it. Notice that there's a downward elevation down to the pump, and then it is pumping it up into reservoir D, which is at quite a bit higher elevation than the pump. So this pump, which is depicted as BC, must deliver 5.62 cubic feet per second of oil, which has a specific gravity of 0.762 to reservoir D. We're given head losses. Head losses from point A to B is 8.25 feet, and from point C to D is 21.75 feet. We want to know how much horsepower must the pump supply to the system, and we're going to neglect this. We won't worry about plotting the energy lines. But we need to calculate the power of the pump. And so we have our information here. We're going to use a nominal density of water for our specific gravity calculation of the oil so that we can get the density of the oil. And what you should realize by now is that we're going to need to solve this using the Bernoulli equation. So this is our general form of the Bernoulli equation. Energy at position 1 plus the head that we add, the head that's lost, minus the head that's extracted. Adding is usually by pumps or compressors. Losses are by friction. Extraction, this refers to turbines. We don't have any turbines. We don't have to worry about that. So that is equal to, all of that is equal to the energy at position 2. And so in this problem, we've got a decision to make. We want to calculate the head that's added by the pump, which is at BC here. And our decision that we need to make is, should we apply Bernoulli's equation piecemeal across this system, or can we apply it from the beginning to the end? And it turns out we could do it either way in this case. We could do a Bernoulli equation from A to B, B to C, and then C to D, or we could realize that since we have, and it turns out since we have constant pipe diameters, notice these are 12 inches going from A to B, and then from C to D is also 12 inches, we could just apply Bernoulli's equation from point A to point D and be able to solve the problem. So let's do that. And so what we can do then is we can take this and we can apply our assumptions. We're going to apply Bernoulli's equation from A to D. So we're going to call position 1 A, reservoir A, and position 2 reservoir D. So what I've done is I've taken the Bernoulli general form and simplified or expressed a few terms using our assumptions. And so we have P1 over rho oil G plus Z1 is our elevation. Notice that the velocity head was deleted. And why did we do that? Well, that is because our position is the level of the tank of this reservoir. How fast is that level of the reservoir moving? That level of the reservoir is going to be moving extremely slow, essentially zero. And so we can set V1 is equal to 0. Z1 is our elevation, and we'll talk about our elevation was definitely higher than the pump. Head added, we have to include that because we do have a pump. Head loss, we do have head losses. We're told what the losses are, the frictional losses in our pipes. There's no head extracted, of course. And then that's equal to our energy at position 2, which is all the way up here at our reservoir D. So P2, again, since our position is the level of the reservoir, how fast is that changing? That is changing very, very slowly. So our velocity at position 2 is essentially 0, but we do have a significant elevation change, so we need to include that. So I've canceled out a couple of those terms, the velocity heads and the head extracted. But notice that we can also cancel out the pressure terms. And why is that? We can cancel out the pressure terms because both of these reservoirs are exposed to the atmosphere. They have the same pressure, right? Now, what we're assuming is that the atmospheric pressure at this elevation is the same as at this elevation. And so that's a 150-foot difference. And what you'll find is that the difference in the atmospheric pressure between this is minuscule. So we're safe, assuming that the atmospheric pressure is the same here. So these pressure terms are also going to cancel out. And so what we're left with is Z1 plus H pump minus H losses is equal to Z2, because these terms are going to cancel out. Now, the losses were given for each of the pipe sections, and so we need to include the total losses. So that's just a summation of the individual losses in these different sections of the pipe, and that is a head loss of 30 feet. The next thing that we need to do is we need to make sure that we are accounting for our elevation differences consistently. And so you notice that our pump is not given at 0. The elevation is 10 and 50. So I am going to set what I'm going to do is set our elevation, our pump elevation as the datum at 0. So that means Z1 is going to be 40 feet. And if this is 0, Z2 is going to be 190 feet. So make sure you're careful with your elevations. And then what we can do is we can solve for the head that needs to be added by the pump. And so that is simply solving for a head pump. That's Z2 minus Z1 plus our head losses. And we get that our pump needs to add 180 feet. All right. So that is a representation of the amount of energy that needs to be added to our fluid to get it up there. But what were we asked? We were asked for the power, right? And all we have done is calculated what's basically an energy per weight of fluid. And so this is just to remind us how these units work. This was confusing to me at the start, but when I first looked at this, but as you do these problems, it'll make more and more sense. But remember, head is defined as the energy added per weight of fluid. And so I prefer to think of these things in SI units, so I don't have to think about the pounds force and pounds mass and using GC. But if we do this in SI units, head is joules per Newton. And what is a joule per Newton? A joule per Newton, that has units of length. So that's why we have H pump, our head is, and we can put this in meters, 54.86 meters. So let's just put that over there. Actually, we'll just delete that. All right, now we need power. Well, once we have energy per weight of fluid, we can then get energy added per volume. Energy added per volume is equal to the head added per times the weight of the fluid, where the weight of the fluid is rho g. And then power is the energy added times the volumetric flow rate. And so what that ends up being is that if we want to go from head to power, we need to take our head, multiply by rho g. U is the linear velocity, A is the cross-sectional area of the pipe. U times A is simply the volumetric flow rate. And so we can do that, all right? We can do that. We know what first of all, we know what the diameter of the pipe is, right? The diameter pipe is 12 inches. We can calculate the cross-sectional area. We were given, in the problem statement, we're given the volumetric flow rate, right? So actually we didn't even really need to calculate the cross-sectional area, did we? Because we were given the volumetric flow rate. So what we can do then is we can, just as a intermediate calculation, we can calculate the energy added. So that's the head added times the weight of the fluid, so rho g. So that's just an intermediate. But what we really want is we want the power. And so the power is equal to head times rho times g times q. And we do that in SI units. We get a value of 65 kilowatts. In American units, that ends up being 87.5 horsepower. So that is solving this problem. Again, because we had constant diameter pipes, we can apply Bernoulli's equation from A to D. Now, if we did not have constant diameter pipes, if say it was 12 here and 6 here, we would not have been able to do that. We would have had to go from A to B, B to C, C to D. So just keep that in mind. But this ended up being a relatively simple problem once we figured out what was going on, and we get a power of about 87.5 horsepower.